This is lecture with instructions for practical work within the subject data analysis, proximal spectroscopy for building prediction models for soil total carbon content. The exercise for model prediction was based on the one experiment which was done on the Faculty of Agriculture, which objective was to use visible and near-infrared soil diffuse reflectance spectra in the wavelength range from 350 to 2500 nanometers for the prediction of soil properties, total carbon, total nitrogen content, soil pH, and plant available phosphorus and plant available potassium content in terms of variable mineral nitrogen fertilization, which was from 0 to 300 kilos nitrogen per hectare and intensive crop production. This research was based on fertilization experiment where we expect enough variation in the data for building visible near-infrared calibrations, like equation that expresses the relationship between electro-optical parameters and the compound of interest, which is total carbon content and other soil properties. The soil type of this experiment is district stagnosoil, and we achieved this high variability in soil properties on a relatively small area, which was the base for finding these calibrations between optical properties and soil properties obtained by chemical analysis. We did soil sampling after winter wheat harvest on the 30 centimeter depth using semi-automatic circular tractor soil probe. That was the circular line sampling of 0.5 meter radius around the grid node, representing sampling site of 16 sample soil composite. It was described as a point sampling, as the average of the 16 individual samples, so the total number of samples on the experimental area was 200, in the regular grid 15 by 15 meters. For this kind of investigation, where we had high soil variability in different properties, it was a good base to have dense grid. Hyperspectral reflectance measurements were done on the air-dried and gridded soil samples through a 2 mm sieve, and samples were scanned by portable spectrodiometer with the wavelength range in the visible and near-infrared spectra. Samples were scanned using fiber optic probe under laboratory conditions and artificial light source, which is similar as the sun radiation, compiling the most of its radiation in the visible and near-infrared part of the spectra from 300 to up more than 2000 nanometers. In the same time, standard laboratory analysis were done because we need dependent or reference data from the wet chemistry to build calibration model. Total carbon content was determined using elemental analysis and dry combustion method. Before we start to build prediction model, we use data visual evaluations or qualitative evaluation of soil spectra. In this experiment, where we had 10 different treatments of nitrogen fertilization, we grouped our data into higher nitrogen level group, described in this graph with red line, and the lower nitrogen level group with blue line. We grouped these data according to the spectral data based on the fertilization levels. We see difference regardless of the multicollinearity we have on these reflectance curves. Lower nitrogen level group is the group where we found the lower level of total carbon content because less of organic matter was developed and remained in the soil because of the lower yield on these treatments. The rule is that soil reflection is higher and increased if the soil organic matter or soil organic carbon content is lower in the soil. For example, this red line is lower, so we had lower reflection when the soil has more soil organic matter or organic carbon content. And this was obtained on the treatments with higher nitrogen fertilization group. In these treatments, we always had higher yield. We can find different absorption features here. For example, in the visible part of the spectra, there is less pronounced concave absorption features for iron oxide content, because this is district stagnosoil and it contains less iron oxide. Stagnosoil has a higher silt and fine sand content, and it has a trace of the bleaching process because of the water stagnation in the upper part. Because of that, the soil is lighter brown color, and naturally it has a lower organic matter content. In this sense, after the more than 25 years of the mineral nitrogen fertilization without calcification, we have situation of decreasing soil pH, and because of that, lowering soil organic matter content. In the visible near-infrared and the short infrared part of the spectra, there are differences according to the organic matter and soil mineralogy, where we see absorption features from the 1800 to more than 2000 nanometers range. And usually that's the reason why we mostly scan the soil in the dried conditions, because water can mask these absorption features. Data analysis, which we use here, this green part is the data analysis I have already done. And this is in the purple color, is what we will do with your task, and I will demonstrate it for total carbon content. I already did data visual evaluation in spectroscopy software. Within this software, I use data formatting and I export it as ASCII as a single output file. Then the same ASCII single output file I import in Excel and I add response variables. You also will have a possibility to see the Excel file where the data is structured and ready to take TXT files as input to spectroscopy software for multivariate analysis. When I sort the data, I save it as TXT file. What will I do here in demonstrating, and what you'll do is to import the ASCII in Parlous, spectroscopy software developed by Viscara Rosell 2008. We will do pre-processing and transformation of the data. PCA is exploratory analysis to reduce the dimensionality of the data and to find the most of the variability. We will use cross-validation to find the optimal model. For predictions, we will use PLSR modeling, validation, and also prediction of the unknowns. The main feature in this data analysis and multivariate analysis is to transform, pre-process, and pre-treat spectra using various algorithms if that is needed to explore our data, to find different solutions, and then to find our final model to implement PCA and PLSR with leave-one-out cross-validation. Prediction file may be imported into Parlous to either validate the PLSR model using an independent data set or to predict unknowns. PLSR has been successfully used in many studies. It is a full spectrum method which combines PCA and multilinear regression in the same, and it was used for prediction of various soil properties from their diffuse reflectance spectra. It is essentially a linear regression technique, but some of the relationships may be nonlinear, and in that sense we can use different transformations and pre-processing of the spectra. Or we can select some specific wavelengths and wavelet ranges specific for some properties to make prediction models and to increase the accuracy. When using PLSR, some weak nonlinearities may be compensated by using few extra latent variables or factors which are obtained by calculated by PCA. Cross-validation is usually used before prediction modeling development to determine the optimal number of factors to the model. This exercise or demonstration will be soil total carbon content prediction. We have a data set of 200 samples. It is split in two subsets, one for training and one for testing the PLSR model for this prediction. 50% of the data were used for training and the remaining half for testing or prediction of unknowns, so 100 and 100. The test data were set aside independent of the training procedure. We use leave-one-out cross-validation to estimate prediction error of model selection, and the maximum number of factor is 20. We use it for testing, and then we will probably reduce this factor when we do PCA and when we find the optimal model, evaluating the root mean square error. It should be the least one, and when we found it, we then select the optimal number of the models. After we perform the PLSR, we do statistical evaluation of predictions using root mean square error and mean error of prediction, coefficient of determination as well. R squared is explained variance of the model. Then we use RPD. This is the ratio of the performance deviation, and which measures the ratio of the standard deviation of reference soil property to the root mean square error of prediction. We can increase the prediction and accuracy compared to using the mean composition for all samples. We classify our model by classification already done by Golizadeh et al. 2018, and we can see these ranges of RPD value. This is the final statistical parameter to evaluate prediction accuracy. Before starting the screencasting from the Parlous, here is the Excel sheet with dataset structure according to the labels. First columns are response variables, 5 soil properties. One I will demonstrate, the other 4 you will do for assignment. From 350 up to 2500 nanometers is the independent data set, which is the soil reflectance spectrum.